This presentation is going to cover an introduction and also an update to our technology. I know some of you may have heard the Ilika story before, but I will be going over the basics just in case any of you are new to the story. So Ilika is best known for its solid-state battery technology. You see a picture of one of our solid-state batteries there next to a euro coin, to give you an idea of the scale of our miniature cells, which have already been launched as licensable products. But the business actually started as a materials innovation business when it was first formed and spun out of the university in Southampton. And we still have a small portfolio of materials innovation projects which we use as the springboard for vertically integrated programs like our solid-state battery effort. Our business model, just to recap, some of you may recognize this from the business model that has been successfully demonstrated by ARM, is a licensing model. Our chairman, Mike Ingalls, was the commercial director at ARM through its strong growth phase, and he has advised us on setting up this business model. Most of the revenue that we're recognizing at the moment is from the front end, so the development programs for which we receive funding from commercial partners and also leverage through some grant funding, which I'll talk about later on in the presentation. And that then flips through into a licensing opportunity when our commercial partners take a license to deploy the technology in the products that they then take to market and pay us a royalty on that's related to the volume of sales that they take through for their applications. How did we get started in solid-state battery technology? Well, Toyota came to us to access our materials innovation platform, which in a nutshell is a way of rapidly making a systematically varying array of functional materials and testing those materials for the characteristics that are useful for the application. So typically, if you're looking at battery materials, you're often looking for materials that have got a high capacity to store electrical current. But actually what Toyota were interested in was making batteries that were non-flammable. So when they first talked to us, there had been an issue with Sony laptop batteries. Those of you who can remember back to 2006 may remember the recall of those laptop batteries and actually virtually prompted Sony to exit the lithium-ion business because of the impact that had on their business. Subsequently, of course, there have been a number of other incidents. It doesn't happen very often, but issues like, for instance, the Galaxy S7 and also the launch of the Dreamliner, they can have a major impact in a business. So Toyota were interested in trying to make lithium-ion batteries that were intrinsically safe, and they do that by removing the liquid electrolyte and replacing it with a solid electrolyte that you can't set fire to. Sounds straightforward. Actually, it's quite tricky, quite difficult to achieve. You need to come up with a series of ionically conductive materials. We spent about 5 years screening those materials and found a subset that have got the right ionic conductivity but electrical insulating capabilities so that the battery doesn't short. In the course of doing that, we also actually identified that there were some other advantages to going to a solid-state device, and they're summarized on this slide here. So first of all, you find that actually the cells can be cycled for a greater number of charges and discharge cycles, which effectively means that the battery has got a longer lifetime. So, typically a standard lithium-ion cell, you can charge and discharge about 1,000 times before the performance of the cell starts to drop off. You know that from your ownership of a mobile phone. So after a couple of years, actually the battery starts to die and you don't get quite as much lifetime out of a single charge. Secondly, solid-state cells are smaller. They have a more compact design, and so that's useful when you want to have a mobile application or where you have limited space to deploy your energy storage capability. Then they've got a low leakage, which means that they can hold charge for a longer period of time. And also they've got a higher power density, which means that you can charge and discharge them more rapidly. So there are some difficulties in scaling up this technology. It's not all good news, otherwise, of course, we'd all be owning solid-state cells right now, and I'll come back to this point a bit later on. But the voyage that Ilika has been on has been one where we've moved from our high-throughput screening, and there you can see one of our screening chips on the bottom left, through the selection of solid electrolyte materials into our first thin film cells, and more recently deployment in larger format devices, in particular for automotive applications. And I'm going to talk about that towards the end of the presentation. So we have a well-defined product roadmap. The ones with the green triangles are the ones which are fully defined, qualified IP products that are available for license. That's the Stereax M250 and the P180. And then we've got some that are still in development, which are the ones that have got the white triangles beside them. So they will be future product launches and are often the subject of project developments, such as the ones that we've recently announced about Goliath. There's also, of course, been in the spirit of continual improvement, a gradual, let's say, improvement of the qualities of some of the launched products. Those of you who follow our news flow will have seen last month that we announced that we've got a higher energy capacity for the M250, which we've achieved by process optimization, so that we've got a greater amount of energy capacity on a square millimeter of substrate. So the M250 has improved in its energy capacity, its energy density as it's sometimes referred to. And then the P180 is one where we've got a high temperature resistance of up to 150 degrees C, which has allowed us to deploy that cell in some quite aggressive environments, such as the automotive industry. So in terms of the market applications, we've mapped those products onto the market sectors that they're designed for. The M250 is really a sensor powering device, so temperature, humidity, light intensity, perhaps motion, and therefore increasing the energy capacity, which we announced recently, has got implications in terms of the size of the sensor, the amount of power actually that's drawn by that device that you can support. The P180 is heavily differentiated from standard lithium-ion cells, which can go up to about 60 degrees C before they start to swell. If you take a lithium-ion battery to 150 degrees C, you might be lucky enough to witness a thermal runaway reaction, which can be quite impressive. The solid-state cells are very stable under those conditions and will continue to function. In fact, they even work better at elevated temperature. Millimeter scale devices are really most useful for medical devices. That's because these are typically implants, and we're going to talk about some of the deployments that we've got there. Clearly, the smaller the footprint, the more useful the battery is, and again, that's a strong differentiator relative to standard coin cells and other lithium-ion cells, because there's a sort of manufacturing limit below which the manufacturing processes aren't really useful when you're trying to encapsulate a liquid electrolyte. But you can take one of these solid devices down to the millimeter scale and implant them very readily. Effectively, you use a microfabrication or a photolithographic process in order to make these millimeter devices. And then Goliath, well, that's all about large format devices. And in fact, there's a switch in process platform you need in order to make them. And I'm going to cover them a bit later in the presentation. So we've made devices that can demonstrate the function of these cells because on their own, batteries are a bit inert. It's quite good to integrate these cells with energy harvesters and the electronics that they power in order to demonstrate the function. So we have a range of demonstrators that you can see on our website. There's some videos with a little bit of entertainment value that shows how these devices work in the real world. And that's useful for us to attract industrial partners who might be interested in seeing how their electronics can be integrated with these devices. So the 3 deployment programs that we've announced with commercial partners, first of all, the medical market is very important for us. Miniature medical implants is a collaboration that we've announced with an international medical device company. This is focused on bioelectronic neurostimulators, but there are other applications also that are in our pipeline in this broad sector. Things like blood pressure monitors, CRM devices, also hearing aids, which of course, if they're implanted, need to be particularly small. So there's a number of devices there that are currently being trialed. Then we have transportation. The real driver here is that vehicles are becoming increasingly instrumented. So, if you've bought a car in the last few years, you've invested in a lot of electronics. Typical modern vehicle has got about 100 sensors built into it. And this means there's a tremendous weight of cabling associated with that. So if you can go to a wireless device that's intrinsically lighter, then that's a real advantage in terms of fuel economy for the vehicle and also cost. So we have a collaboration with Lightricity, which is a spin out from Sharp Laboratories here in the UK, and also McLaren. And then on the industrial side, Titan Wind is one of our showcase collaborations. Titan Wind is China's largest wind turbine manufacturer. Actually, they're visiting us later in the week, and they're interested in condition monitoring of turbine blades. So we combine these batteries with strain gauges and piezoelectric energy harvesters to make sure that we can tell when the blades of a wind turbine are starting to fail and deploy a maintenance crew to fix that before it becomes a catastrophic incident. So the question I often get is, well, what's the commercialization progress? We've seen an uptick in revenues in the recent financial results, and we expect that to continue in line with analyst forecasts. But this uptick is typically associated with the development programs that we're engaged with. You can see what we've plotted here is actually a number of agreements to give you a feel for the progress that's being made there, plotted over the last couple of years. We've got NDAs in the dark blue segment at the bottom, then materials transfer agreements in the middle section, culminating in R&D programs and also licensing proposals at the top. And I think it's a decent lead indicator that the revenue that we are recognizing from those R&D programs has doubled at our last financial results and is expected to increase again in the current year. So in terms of where these batteries are being sent, what type of companies are using them, and whereabouts they're located, first of all, the majority are going into medical device organizations. You see just over half are being evaluated and sampled by them. In fact, the majority of those companies are in the US, and that's why the geographic distribution of these cells has got a similar shape. Industrial accounts to about a quarter of our pipeline. So these are applications like the Titan Wind application and also automotive. A lot of them are in Europe actually, but also in Asia. And then IDM stands for Integrated Device Manufacturers. They are organizations that take components and actually make a device which can then be integrated into full products later on in the supply chain. And I've grouped them together with foundries, which is where these cells can be made. So that's the overview of where we are with the thin film devices, the micro batteries. Let's talk a bit about the Goliath program, which has had quite a high profile in the media in recent months. I guess, this is driven really by some of the legislative changes that we've seen around the world, where governments are promoting the use of electric vehicles. This program is at a lower technology readiness level than our thin film battery program, but nevertheless, I think is of pretty strong commercial interest. There's a series of proof points that I point to here, but I think industry consensus in the automotive industry is that solid-state cells are the natural successors to lithium-ion cells, and that we will see this transition to solid-state in the middle of the 2020s. So most of the automotive OEMs and tier 1 battery suppliers have got solid-state batteries on their roadmaps now and are investing in the technology. And that's good news for us, of course, because we're interested in licensing our technology into those programs. What's also helped is that the UK government has launched the Faraday Battery Challenge. Actually, that's a commitment of 246 million over the next 4 years, covering not only cell manufacture, where we're interested, but also some of the pack design. So it's an integrated approach that goes across the whole supply chain. 80 million of that is going into a facility in Warwick, close to where JLR has their headquarters. So they're quite closely involved in some of this scale-up. And in the summer, we announced that we'd received 2 significant grant offers from the Faraday competition for 2 programs. The first one called Powerdrive Line, and the second one called Moses. So Powerdrive Line is all about rapid charging for electric vehicle batteries. A sub 25-minute target is what we have in mind. Typically, actually, this charging rate damages batteries unless it's managed effectively in a BMS. Cells don't really like to be charged that quickly. Solid state has got the advantage that they've got this higher power density that I referred to earlier, and therefore can accept higher charge rates. We're the lead partner in this program, together with Honda UK, based in Swindon, Ricardo, who most of you will know is an automotive design consultancy, CPI, and also UCL here in London. And so that program's already kicked off. We announced that last month, and that's making good progress already. We were also able to accept a second program. Originally, these programs were submitted so that they stood on their own 2 feet, because we weren't sure we were going to get both of them. But we've restructured the second of the grant offers so that financially we can support our own contribution to this. And this is a consortium led by McLaren to build high-performance cars, and also involving A123 batteries, which some of you may know is a US-headquartered, Chinese-owned lithium-ion battery manufacturer. They already have manufacturing facilities around the world, and we expect this program to kick off by the end of the year. So I guess the basic message is plenty of support to leverage shareholder equity that we're investing in this area. And the basic change here that I'd like to point out is that we use a thin film deposition process in order to make the micro batteries, the original Stereax cells for IoT. We're actually using the same materials platform for these larger format cells, but we're switching the process platform from a vacuum deposition approach to a cheaper printed approach. And that may seem a subtle change, but actually it's got a big cost implication. It allows us to get down to a cost point that is useful for large format cells for the automotive industry. So what does the route to commercialization look like? We are establishing a pre-pilot plant at our facility in Southampton for making these large format cells, where they'll be evaluated and tested in these programs that we've got supported by the Faraday Battery Challenge. The next scale up we expect to be supported by Innovate UK, perhaps through that £80 million investment that's going into a battery manufacturing center in Warwick, and then ultimately licensing that into an automotive JV when it gets through to full commercialization. So we're still pursuing a capital light model without the need to invest in all of the infrastructure associated with manufacturing these cells at volume. So I brought along Steve with me tonight, and he's going to talk you through our financials just to let you have some insight into the scale of the business.
Hi, this is a very high-level summary of the last 2 financial years in the years to 30th of April. You can see our turnover has doubled, albeit from a relatively modest base. We are still continuing to invest in the technology through the development phase, so you see a modest increase in our expenses, a lot of which qualifies for R&D tax credits. So we actually receive just under £500,000 back from government in tax credits, and you can see that's reducing our loss for the year. Analyst forecasts for this financial year, which we're just about halfway through, are that our turnover will increase again by about the same amount, up to about 3 million, and again the loss will reduce. You can see the cash on the balance sheet at the end of April was about 2.8 million. That is about 2.6 million you see as cash burn from 2017 through to 2018, so that would suggest about a year's cash. Clearly we're reducing that burn rate as turnover increases, but we've also supplemented that balance with a fundraise post year end. So in July we raised a net 4.1 million, which obviously helps support the balance sheet and give us a bit more working capital, but also to support those grant funded programs that we've just received from Innovate UK. So that's the basis for that fundraising, so that should see us through to break even.
So just a quick whip through some of the milestones that we've achieved over the last year or so. In 2017 we spent a lot of time reinforcing the IP portfolio with 4 additional patents filed. We now have a family of around 30 patents, and they're filed in the key jurisdictions where our battery technology is targeted. We launched the P180, which is that high temperature industrial thin film battery. We announced the 2nd and 3rd of those 3 deployment partners that I was talking about earlier in the presentation, and we engaged with about 40 potential licensees in the course of 2017, which took us up to a total of about 80. In this year, Steve kicked it off by leading the ISO 9001 certification. The reason that I mention that is that, of course, we're engaging with industrial partners who have quite sophisticated quality systems, so we have to be able to match that. So that's why we spent the time to qualify our own processes and get that certification. As Steve mentioned, we did double turnover. We were awarded this 4.1 million by the battery challenge, the Faraday battery challenge. Just last month we shipped pre-launch millimeter scale cells. Some of you may have seen the RNS, I think it was an RNS reach actually on that, through to medical device companies in the US and Asia. So that's really an indicator that we're getting close to a full commercial launch of that product. And over the last few weeks, we've announced increased power and energy densities from our thin film batteries, which enables a greater range of the devices that we're able to support. So what can you look forward to happening over the coming period as we look at the next 6 months towards the end of this financial year for us, which ends at the end of April? Well, we're looking to secure additional Stereax development partners, and we will be announcing some of those, probably increasingly commercial as opposed to grant-funded interactions, often in foreign jurisdictions, and that will be a segue into some of the initial licensing partnerships that we're targeting. We'll also be commissioning the Goliath pre-pilot line, which, as I said, is a separate printing process platform, different to the vacuum deposition platform that we've got operational in Southampton. We'll be launching another Stereax product related to that millimeter scale technology and pushing towards recognition of that material increase in turnover. And what I haven't got here actually is that another piece of the jigsaw puzzle will be the manufacturing partnerships which we're chasing, because a lot of the OEMs who are likely to take licenses will not be manufacturing themselves, and so therefore we're pre-qualifying manufacturing organizations so that they can take orders when these products go into production. Thank you for your time.
Thanks for that, Graeme. It's good to see you still making progress. I just, at this stage of development of the business and the technology, there's two areas that concern me, and I guess you, is what do you now across the landscape see as the sort of most worrying competing technologies that may stymie your ability to gain market share in these kind of applications? So that's the first one. And the other one, of course, is within the kind of battery technology that you're developing, who do you now see as your most threatening competitor?
Good questions, thank you. So first of all, the competitive landscape never stays still for very long. And actually, you know, incumbent lithium-ion cells have become increasingly competitive in terms of their performance, their properties. So there has been some miniaturization progress. The areas that we are targeting typically tend to be areas where you can't use the incumbent technology to address the problem. So that's why you'll hear me talking about these millimeter scale batteries for medical devices, because actually you can't miniaturize standard lithium-ion technology down to that scale. So therefore, you know, we're sort of pushing into blue water territory. And secondly, the high temperature applications where lithium-ion cells become inoperable due to the evaporation of the liquid electrolyte, so above 60 degrees C. So that's why I often talk about industrial deployments. But nevertheless, you know, some of the lithium-ion cells are getting quite small. You can get, you know, button cells that are rechargeable. They often have leakage currents, though, that mean that when we're using an energy harvester, we can beat them on that particular front. In terms of competitors, I'd say that, you know, globally, actually Ilika is very well known for its thin film Stereax miniature cells. There have been some companies who have tried to launch products actually unsuccessfully because they fell down on various technical criteria. So increasingly, I think we're being seen as the go-to company. For the larger format cells, that portfolio of would-be competitors is perhaps larger, but actually the diversity of technical solutions is perhaps larger as well. So you see well-funded, privately held US startups in the area like Solid Power and Ionic Materials. You may have seen them in the press. We have a differentiated solution. You know, they have different chemistries, which they've also patent protected. But, you know, there will be some consolidation and a bit of a shakeout in that space as we move through the technology readiness levels through to commercialization.
With lithium, we've heard there's a lot of shortages potentially with lithium coming. If I understand you correctly, your product doesn't use lithium. Could you explain a bit more fully what materials your product uses and other supply problems potentially if the volumes go up in the future?
Yes, good question. So actually, our product does use lithium. It is effectively a lithium-ion based device where lithium ions are moved from one electrode to the other as you charge the cell. Actually, there is a huge amount of lithium on the planet. However, I would agree that there appears to be a supply shortage of lithium simply because of the speed at which the resources can be exploited. So the majority of the Earth's lithium resources are actually in Bolivia and Chile in high altitude evaporite deposits, which are effectively high altitude lakes where the water is evaporated and left behind a sort of salt crust on the surface of the desert. And this can be mined very cheaply, actually just by scraping the surface. And there's been a bit of a rush to try and grab those resources while they're still so obviously available. But lithium is the third lightest element in the universe, and the rule of thumb is that actually the lighter the element, the more abundant it is. So there is loads of lithium on the planet. Cobalt is perhaps one that's been in the news recently, not perhaps helped by the latest Ebola outbreak in the DRC, which has fueled concerns about that supply. One of the advantages of solid state is that it actually allows you to use other cathode chemistries that don't rely quite so heavily on cobalt. So it is quite interesting in that regard.
I was very excited to hear about the recent announcements about your threefold increase in Stereax power. What's the commercial significance of that, and when do you think you're going to announce your first license deal then, Graeme?
Yeah, I think that's a great question, Mark. I think that the power density of these cells increases the range of devices that you can power. So we announced that, in fact, our thin film devices can now be discharged and charged at a rate of 20 C, which in layman's terms means that the entire device can be charged in 3 minutes, which makes them pretty useful for some of the applications where you need to perhaps transfer data with a chip that's quite power hungry. A lot of these batteries are used to power electronics with microprocessors and radio chips in that give you a spike in power demand. And making these devices more robust in that type of context actually means that the integration of the devices into different products becomes more straightforward. You're less likely to find that the batteries can't deal with the rugged operating conditions that you sometimes come across. So you can see that actually our pipeline's looking pretty ripe in terms of commercialization. Historically, I've been pretty bad at predicting when our first licensing deal is likely to land. Hopefully that's improving as time goes on, but I can tell you that we've got some proposals out there that we are currently negotiating. So I expect some further progress on that front shortly.
Well, I'm struggling to see how your current cash resources are going to see you through to break even.
Yeah, Steve, do you want to handle that one?
Sure. So there's 4.1 of funding from Innovate UK, to which we have to make a contribution as well for those programs. But we are looking to get funds from the initial licensing deals. So those sort of upfront licensing payments will support the cash balance and take us through to profitability on the build-up of those.
You also did a funding there recently.
Yeah, so we've got the additional 4.1 since the year end. So we've got about just under 7 million effectively. We've used 6 months worth of cash from then, so we're probably about 1 million down from that, and then that burn rate is reducing as we go forward.
Just looking at the timelines for the various products.
Well, the timelines for Goliath certainly are a number of years, but for the miniature batteries, we're at a stage now where we've got a high technology readiness level, and we're looking to license those now. We have finished products, defined products, and new products about to be launched. So we're very close to those.
Just one quick question. You've got a manufacturing facility that you've developed so you can actually sell something. It's supposed to be a licensed model. At which point does what overtake who? Are you going to go on manufacturing? Are you going to rely on your licensees? Or is the manufacturing largely to prove the process?
That's exactly it. Is that the production line that we've got in Southampton is really a pre-commercial production line. And it's to demonstrate that the IP is licensable, because you need to be able to send out samples to customers so that they can test it in their products. Really, we need to get to the volume of manufacturing that gives you a low enough unit cost to be able to address the markets. And that's another step up. So that's why we're pre-qualifying these foundries, so that technology transfer is as smooth as possible.
Does that have to be pre-qualified for every chip? For every battery? There's all those white triangles need a separate production line?
No, actually, the process is a common process. So it's a vacuum deposition process. We actually use either physical masking or photolithography to make the different devices. So that means that once you deposit onto a wafer, you can effectively determine the architecture with your back-end processing. So, you know, it's a common platform. Where we are switching the process platform, which does involve a different process, is for the Goliath cells, which are printed.
Do your customers or partners ever offer to buy the IP or buy the company?
Yeah, well, if that did happen in terms of buying the company, we would have to announce that pretty quickly. You know, I think I wouldn't rule that out going forward. That we have got a lot of industrial partnerships going, and you know, I know that it does cross their minds sometimes. So that wouldn't be a surprise if at some point we had an offer like that.
Fantastic. Graeme, Steve, thank you very much indeed. Very
Thank you.
interesting.